Hey physics students, so in our last lesson we talked about position and time, and we made graphs of position versus time, and we saw that the slope of that graph is the velocity of our object. Now today we're going to talk a little bit more about velocity, and we're going to make some graphs of velocity versus time, and we're going to see the slope of that graph also has a special meaning. It's called the acceleration. So today we're going to talk a little bit about velocity, and we're still working on the target of being able to describe the relationship between displacement, velocity, acceleration, and time. So let's go ahead and talk about some of that stuff. Alright, in the last video, position versus time, we talked a little bit about velocity because it was the slope of the line on a position versus time graph. Some things to remember about the velocity: we use the variable v, lowercase v, to stand for velocity, and we measure it in units of meters per second. To calculate the velocity, we can take the displacement, delta x, divided by the time, delta t, and that's where we get the units meters per second. This displacement is measured in meters, and time is measured in seconds. So meters over second, meters per second. Okay, a couple other things to be aware of about velocity. Velocity can be either a positive number or a negative number. Right? What does it mean for it to be positive versus negative? A positive velocity means your object is moving in the positive direction. It's moving, usually maybe we might call it forward or up. Some direction that we call positive. You'll have a positive velocity. And a negative velocity would mean just the opposite. It's moving in the direction that we call negative. It's moving in the negative direction. Maybe backwards or maybe down or something like that. Okay? Now, just like displacement, velocity can change over time. Usually in our everyday language when we talk about this, we call it either speeding up or slowing down, right? If the velocity is getting bigger over time, we say it's speeding up. If it's getting lower over time, we say it's slowing down. So a velocity can have a starting velocity, an initial velocity, and a final velocity, just like a lot of the other things that we've talked about. So if we want to talk about an initial velocity, we can use v with a little subscript I. And then if we want to talk about a final velocity, we can use v with a little subscript f for initial velocity and final velocity. And just like the displacement and just like the time, we can find the change in velocity. The change in velocity we could call delta v. Remember, delta means change. And we can find that by taking the final velocity minus the initial velocity. So that would be Vf minus Vi to find the change in velocity. Okay, just like with position and time, I can make a graph from velocity and time, right? If my velocity changes over time, a graph can help me see how my velocity changes over time. And these graphs of velocity versus time are different than the graphs of position versus time. They're a different kind of graph, and the lines on them mean something different, okay? So here you can see I've drawn a velocity versus time graph. And just like with the position versus time graph, the thing I listed first in the name is the thing that goes on the y-axis, right? So velocity versus time should be velocity on the y-axis and time on the x-axis. Okay, if you take a look at my graph, I have three sections on here. I've labeled the first part A, the second part B, and the third part C, right? And if we look at these, they mean something a little bit different than they did on the position versus time graphs. Let's start with maybe the most obvious one here, section B. If this was a position versus time graph, what would that flat line mean on the position versus time graph? That would mean that my object wasn't moving, right? But here on the velocity versus time graph, it means something different. This object at section B here, this object was moving, and it was moving with a velocity of 20 meters per second. But its velocity wasn't changing. So on the position versus time graph, that flat line means that the position isn't changing. On the velocity versus time graph, that flat line means that the velocity isn't changing. It can be moving, but the velocity isn't changing. It's a constant velocity, right? Now, let's look at some of the other ones. What does it mean in section A here? We can see that my line is going up. So what does that mean? That means my velocity is changing. The velocity is going up over time. So in these 10 seconds, my velocity went from 0 to 20 meters per second. Was the position changing? Of course it was changing, yes. My object was moving. Was the velocity changing? Yes, that's what my graph is telling me. It went from 0 to 20 meters per second. So was my object speeding up or slowing down? Well, if I went from 0 to 20, it was speeding up, right? So when I see an upward slope like that, that tells me my object is speeding up. And we have a special name for that. We call it acceleration. We'll talk a little bit about acceleration in just a minute here. Okay, look at section C. You can see in section C, my object went from this velocity, which was 20 meters per second, and it went down to 0 meters per second. So was my object speeding up or slowing down? It was slowing down, right? So when I see a downward slope like this, a negative slope, that tells me that my object was slowing down. So on a velocity versus time graph, a positive slope, my object was speeding up. A negative slope, my object was slowing down. And if the slope is 0, the velocity isn't changing. You see, it's a constant velocity. Now let's take a look at what that slope means. Just like the slope on a position versus time graph, the slope on a velocity versus time graph has a special meaning. Okay, let's think about the slope for a minute here. Okay, the slope is the rise over the run. Let's see, what does the rise really mean? The rise is the change in what's on the y-axis, right? It's the change in what's on the y-axis. Well, what's on the y-axis is velocity, right? So the change in velocity. How can I write that with variables? Change in velocity. Change is delta, and velocity is v. So the rise, the change in velocity, we call delta v. Okay. What about the run? Okay, the run is the change in what's on the x-axis, right? The change in what's right here. What's on the x-axis is time. So the run is the change in time. How do I write change in time using variables? Well, change is delta, and then time is t. So the slope of the line on our graph is delta v over delta t. It's the change in velocity over the change in time. Okay? And we give this a special name, a special meaning. We call this the acceleration. Okay? So acceleration, we use the lowercase a for acceleration. So the acceleration is the change in velocity divided by the change in time. Let's talk a little bit about acceleration here. Okay? So keep in mind, this is the slope of the line. Okay? So what happens when I have a positive slope? I have a positive acceleration. My object is speeding up. A positive acceleration, speeding up. What does it mean for it to be negative? Well, that means the slope is negative. What's going on when the slope is negative? The object is slowing down. So a negative acceleration means the object is slowing down. What about a flat line on my graph? That would be a slope of 0, right? If the slope is 0, then the acceleration is 0. That means my object's velocity is not changing, right? So my object can speed up, slow down, stay at a constant velocity. A positive acceleration means it's speeding up. A negative acceleration, it's slowing down. 0 acceleration means it's a constant velocity. So here we have an equation. We can find the acceleration. We can find it from the slope of a graph, or we can find it using dividing two numbers, right, with this equation. Now let's think about the units for acceleration for a minute here, okay? The units for acceleration, we've got delta v, velocity. What unit is velocity measured in? It's measured in meters per second. And then on the bottom here, we've got time. What units is time measured in? It's measured in seconds. So on top I've got meters per second, and on bottom I have seconds. So the units for acceleration are meters per second per second. Sometimes we'll write it like this. Sometimes we'll write meters per second like this. But most often we'll write meters per second squared. So sometimes when you type, like particularly in like a Google form, it's hard to put a squared in a Google form. I'll probably write meters per second in a Google form. Otherwise, write meters per second squared. Sometimes you'll see people represent it like this: meter per second with a little -2 there, right? And you know the negative exponent means this thing is in the denominator. So meter per second squared, it's meters per second squared, like this. So any of these will be appropriate to write for the units for acceleration. They all mean the same thing. This is the one we'll write most often, but you might see this one in a Google form because it's hard to put a squared there, right? So the units for acceleration, meters per second squared. Okay, just for a minute, let's talk about what happens if we see on a velocity versus time graph a line that is not a straight line, right? With a straight line, we know what that means. The slope of that line is the acceleration. But what does it mean if the slope isn't constant? What does it mean if my line curves? Well, this is hard for us to deal with if we don't know calculus. Okay, calculus would let us deal with this. This would mean that there would be a change in the acceleration. A change in acceleration in physics is called, it's got a fun name, it's called jerk, right? But we're not going to go there. We're going to limit ourselves to straight lines on these graphs because we don't know calculus yet, right? At least most of us don't. We would need some calculus to deal with that. So we are not going to deal with curved lines on the graph. But let's take a look at, we can answer some other fun questions with our velocity versus time graphs. One other fun thing that we can do with these graphs is, not only can we find the acceleration, not only can we find the change in velocity or how much time has gone by, there's a lot of things that we can find on a velocity versus time graph. But one thing you might be surprised to find is that you can find the displacement. You can find delta x. How far does the object from where it started? Let's say I'm looking at this and I want to know how far is the object, what's the displacement after 2 seconds? Okay, you can see at 2 seconds, my graph goes up from 0 to 2 seconds, and then it flattens out right there. Let's take a look at how do we know how far the object is gone in those first 2 seconds, okay? If you know calculus, you already know this, but the area underneath that line is how far the object is gone. So if I look at the part of the line just up until 2 seconds, area underneath the line right there is how far the object has gone. So let's see, can we find the area of that space right there? You can see what shape it is. That's a triangle, and you know how to find the area of a triangle, right? The area of a triangle is 1/2 times the base times the height. Some people learn base times height divided by 2. Some people learn 1/2 times base times height. It's the same thing, right? So let's take a look. Do we know what the base of that triangle is? Well, it's 2 seconds, right? From 0 to 2 is 2 seconds. So this will be the displacement. It'll be 1/2. And by the way, when you see a number that's already part of a formula, you don't need to count that for significant figures. This is not one significant figure. This is more like a counted number. It's an infinite number of significant figures. Okay, so my base there is 2 seconds. And can I figure out the height? See, it goes up to here. It goes up to 2 seconds. It goes from 0 to 2 seconds. So the height is 2 seconds. So if I multiply this, my displacement, 1/2 times 2 is 1, and 1 times 2 is 2. So at that point, how far is my object from where it started? Displacement is measured in meters. So 2 meters from where it started. If you need to know the whole thing, then we can break it up into parts, right? So we found this part. What if I wanted to know how far is it from where it started? 4 seconds. So 4 seconds here. We had this triangle, we just found its area. Now we have this square, we can find its area. This is a square, right? It goes up 2 and it goes over 2, so that is a square. So the area of a square is just the side squared. The side is 2, so 2 squared is 4. So the area of the square is 4 meters. So how far did it go after 4 seconds? Well, it went 2 meters. here, and then it went another 4 meters, so it will be 6 meters from where it started. So there, delta x would be 6 meters. Alright, so there we talked a little bit about velocity. We talked about velocity versus time graphs, how they're different from position versus time graphs. We talked about what the slope of a line on a velocity versus time graph means. It means it's the acceleration. Talked a little bit about acceleration. We use the letter A to stand for it. We measure it meters per second squared. And we talked about how to find the displacement from a velocity versus time graph. So hopefully that helps us to be able to describe the relationships between displacement, time, velocity, acceleration. So until next time, take it easy.